Hello, everyone. My name is Gary O'Mealy, and this is Chapter 1 of Flight Physiology and Human Factors, and we are going to take a look at the aviation safety record. And one of the major things we are going to try to accomplish in this chapter is understand the safety context out of which the discipline of human factors in aviation arises. So, more than anything else, you're asking, why do I have to take this class? Well, what we need to understand in this chapter is we need to compare the safety record of aviation against those other modes of transportation like driving, taking the train, taking a boat. You've heard your whole life that flying is the safest way to travel, and that's absolutely true. But at the same time, air travel is not 100% safe. Nothing is ever going to be 100% safe. Accidents do happen. So we also want to understand the types of aircraft accidents that do occur and the types that are statistically the most likely to occur. And once we get through that, you're going to understand why you're having to take this class, because, not to give away too much, but we are going to find that pilot error, mismanagement of resources, poor decision making, lack of skill, these are all things that are disproportionately most likely to cause an accident. And that's why we need to study the human body. We need to be aware of what we're capable of and what we're not capable of so that we can make the proper decisions when we are in the aircraft. So, like I said, no mode of transportation is going to be 100% risk-free, but flying does represent the safest option for sure. So about 95% of transportation fatalities occur on the road, and aircraft fatalities only make up a very small percentage by comparison, only about 0.15%, which is about 15 out of every 1,000. So if we split aviation up into two categories, being general aviation and commercial flights, and we'll better define these here in just a minute, most of these are going to occur in the field of general aviation. So there's lots of reasons why commercial flying is quite a bit safer than general aviation, and we will touch on that a little bit later. So civilian aviation, like we just said, is divided up into two categories. We have general aviation. This is all civilian, meaning non-military flight operations other than scheduled commercial air passenger and or cargo service flights. So this can include anything from recreational flights, sightseeing, instructional flights, corporate transit, and on-demand charter flights. And then air carriers are going to consist of two basic things: the airlines and cargo service. So you're either talking about, for commercial airlines, you're talking about flights from Los Angeles to New York, and there's 300 people on board. Cargo service is going to fly very much the same kinds of planes, these very large turbojet planes, but they're going to be the ones that, like, say, FedEx or UPS on the side. They're not really carrying people so much as they're carrying cargo. So, of the roughly 600,000 certified pilots in the United States, about 500,000 fly general aviation aircraft. So, disproportionately, if you consider the entire fleet of aircraft in the United States, most of them are GA aircraft rather than commercial fleets. So the conclusion based on this that we can make is, just based on the number of takeoffs and landings, aircraft incidents and accidents are much more likely to involve GA aircraft just based on volume. So there's a lot more GA aircraft, and they're doing a lot more takeoffs and landings. Their flight times tend to be a lot shorter than what you see with air carriers. So just based on those data alone, it just seems much, much, much more likely that you're going to have accidents, incidents, whatever you want to call them, with GA aircraft versus commercial aircraft. But what we're going to see here is that it's not just a volume issue. The GA sector does have a higher accident rate than the commercial sector. So let's talk about that a little bit. So we need to talk about safety in the GA sector versus safety in the commercial sector. There's actually several good reasons why the commercial sector has such a great safety record compared to general aviation. Number one, There are extensive and regular training programs available and required of commercial airline pilots that are not required of or maybe available to just regular GA pilots. Number two, we have routine high quality maintenance on higher end multi engine aircraft. So not only are the commercial fleets flying much larger, much safer, much more sophisticated machines, those machines are being tended to in a much more careful and much more regular and much more methodical way than, say, just a Cessna that's sitting in a hangar at the airport. Commercial airlines tend to have larger flight crews, so 2 or more experienced pilots. Whereas it's possible for a GA pilot to just hop in his airplane and then go fly solo. So, what that means is that for the GA pilot, if he or she is all by themselves, there's a lot of decision making, tasks that need to be accomplished, some of those being mental tasks. So it is all on that person to always make the right decision, make the right reaction to given visual references and things like that. Whereas on the commercial side, because you have 2, 3, or even 4 people in your flight crew, there is communication back and forth. Everybody is a part of the decision-making process. There are checklists that everybody can run through to make sure that everybody is making the right decisions at the right times. As you can, I'm sure, imagine, the commercial side of things has a much stricter regulatory environment, aka the rules. And then number 5, there tend to be life-saving technologies on board commercial flights that are just maybe not present in GA aircraft. Things like collision avoidance technology, terrain detection technology, and things of that nature. So if we want to kind of focus on some of the commercial regulations so that we have a better understanding of why commercial aviation just tends to be so much more overwhelmingly safer, they have standard operating procedures, and these kind of manifest themselves as checklists that basically spell out a step-by-step list of instructions for every phase of flight, and this is intended to minimize the risk of missing important steps, skipping important steps, misreading or misinterpreting certain steps, and this is where having a larger flight crew also lends itself towards being a bigger benefit as well. If you have multiple people as being part of the checking off process of going through these lists, that minimizes the risk of error, and it won't totally mitigate the possibility of an accident, but it will greatly reduce it. There is what is called the sterile cockpit rule, which prohibits non-essential activities. Usually you're talking about things like chit-chatting, shooting the breeze, things like that, during critical stages of flight. And usually by critical stages of flight, we're talking about altitudes that are below 10,000 feet. So once you're up at cruising altitude, the sterile cockpit rule doesn't really apply. But when you're that close to the terrain, you have to be basically laser focused on what you're doing, your bank angles, your flaps, and things like that, to make sure that you are doing, from a regulatory standpoint, all the right things to ensure the safety of the crew and of the passengers as you fly. There are safety management systems, so airlines have safety departments that ensure proper and regular training for pilots and crew to make sure that when you're talking about things like rules and regulations and standard operating procedures, everybody knows what they're doing, what they're supposed to be doing, and how to do it. So the strict regulatory environment of commercial flight is meant to mitigate problems that result from human limitation and error. So the biggest takeaway that you're going to have from this chapter is hopefully going to be, if there's going to be an accident involving an aircraft, it is overwhelmingly likely that it is going to be because of the actions or inactions of the pilots involved. We tend to sometimes think about airplane crashes or airplane incidents that involve mechanical failure, an engine flaming out on you, like hydraulics going out on you, the tail falling off, the rudder not working. So these are all mechanical failures that have nothing to do with human limitation and human error. But those things are overwhelmingly much more rare compared to incidents that involve humans making mistakes, okay? So that is one of the most important takeaways that you're going to get from this chapter. It is almost certainly going to be human error that causes an accident versus something like a mechanical issue. So this is a key and critical reason why commercial flight tends to be far less accident prone than general aviation, because of everything that we just looked at in the previous slide. There are steps and regulations and technologies that are in place in commercial aviation to mitigate the possibility of human pilot error becoming a causal factor in an accident. So if you look at this graph right here, these two graphs, the top graph shows from the years 1959 to basically the present. So 2018 is not exactly the present, but this is as far out as this study goes. We can see the prevalence of fatal accidents in commercial aviation over time. Back in the very beginning of commercial aviation, we can actually see that the accident and fatality rate was quite high, but over time, as this regulatory environment has kind of evolved and established itself, you can see that the accident and fatality rate in commercial aviation has become almost non-existent. In fact, in order to get an idea of what's happening here, where everything is so close to the x-axis, meaning 0, we had to blow it up into this figure right here. So if you're not paying attention to the y-axis here, this might look like, oh, well, there's still a lot of accidents occurring. Well, look here. Even in 1999, the annual fatality rate in commercial airlines was only 1%, and it has continued to decrease over time. So now let's switch gears a little bit and talk about the different kinds of aircraft accidents and incidents so that we can better understand what part of those accidents and incidents is most likely to be caused by human error, that is, action or inaction of the pilots involved. Retrospective data on accidents tell us that the defining event of an accident is actually kind of easy to predict. So, statistically speaking, some types of accidents are more likely to occur than others. So the FAA compiles a list of the most common defining events in accidents and incidents. So the most common and most likely kind of accident is called loss of aircraft control in flight, or you can call this lock-eye. Second is controlled flight into terrain, or CFIT. 3 is a system or component failure involving the power plant or engines, so this is SCFPP. You have fuel-related incidents, which we will talk about a little bit later. That's not strictly one kind of thing, but multiple kinds of things. And then unknown or undetermined. So sometimes accidents happen and we just can't really figure out exactly what went wrong. And then there are other defining events in GA accidents and incidents, so it's not just the 5 that we just looked at. The 5 that we looked at on the previous slide are the most common. So there is actually a laundry list of types of defining events or occurrences involving system component failure and that don't involve the engine, unintended flight into instrument meteorological conditions, which basically means that you lose your visual references because it's nighttime or because it's cloudy. Mid-air collisions, low altitude operations, so you're flying a lot lower than you're supposed to, or there's others as well. And to help you understand some of these occurrences and some of these defining events, I posted a PDF of all the different categories of occurrences and defining events on Blackboard. Take a look at that. That will provide definitions and some important context that should help you understand what these things are and why the 5 that are most common that we looked at are the most common. So real quick, let's take a look at loss of control in flight and understand what that is all about. So lock-eye involves an unintended departure of an aircraft from controlled flight. So basically, you lose control of the aircraft for whatever reason, okay? So the NTSB observes that most pilots, in most cases of lock-eye, pilots fail to, 1, avoid conditions that lead to stall, 2, recognize the symptoms of an approaching stall, and 3, use proper stall recovery procedures. Now, of course, we know that stall involves things like loss of airspeed, inappropriate attitude of the airplane. So basically, you get to the point where the airplane cannot generate the lift to keep itself airborne, and it's going to start falling out of the sky. So these three things that you see right here are going to obviously cause you to lose control of your aircraft, okay? But this, again, becomes kind of a training issue. It becomes a compliance issue. Understanding how your airplane operates and how to handle it so that you can mitigate the risk of stall. So, if we're talking here, in other words, this occurrence is an issue of human cognition and decision making, okay? So, when you're learning to fly, you learn all about aerodynamic stall and how to avoid it at all cost. What sorts of things should you be doing to avoid stall? What sorts of things should you not be doing to prevent yourself from stalling? So again, this becomes an issue of human cognition and decision making, which we are going to eventually see is a human physiological issue. You need to understand how your body operates and how your brain works so that you can understand, okay, I may think I can get away with a certain attitude or a certain bank angle or a certain airspeed so that I won't stall, but your brain is flawed. That's kind of the main thing I'm going to try to get across to you in this class. The human body is an amazing thing that's capable of amazing feats, but the human body is flawed, okay? So if nothing else, you need to trust your training and trust your instruments. They basically are going to know better than you. Okay, so let's lay out a couple of definitions so that we can understand the sorts of contributions that different conditions make to the two most common types of aircraft defining events, lock-eye and CFIT. So the first definition we're going to have is VFR, which stands for Visual Flight Rules. So this is going to involve the pilot maneuvering the aircraft by using visible landmarks such as the horizon and objects on the ground. So basically, visual flight rules are going to be applying in visual meteorological conditions, which is a meteorological state in which outside references are readily visible and VFR can be conducted safely. So another way of putting this is that VMC is in effect when you have a clear day outside, it's daytime, the sun is shining, you can see the horizon, you can see objects on the ground. You basically can use your eyes and know that you're at level flight with the horizon. You know you're not about to fly into a mountain. You know you're not about to crash into the ground. So when VMC is in effect, you can fly by visual flight rules. So that's a safe thing to do, okay? So if VMC is present, then a pilot can fly by VFR and avoid both lock-eye and CFIT rather easily. But the question becomes, and this is going to be kind of a common question for us in this chapter, what if VMC is not present? So when a pilot attempts to fly by VFR in conditions of low visibility, meaning not VMC, so it's nighttime, it's overcast, you can't see the horizon, you can't clearly see objects on the ground, that's called IMC, or instrument meteorological conditions, you increase drastically the chances of something happening called spatial disorientation, in which you're flying your airplane, but you don't really have any sense of where you are, whether you're flying level with the horizon. You could be flying straight, you could be flying straight towards the ground. You're not necessarily going to know. So if a pilot is only rated to fly by VFR, we want to minimize the risk of spatial disorientation by making sure that we're only flying in VMC. Once you lose those visual cues, the horizon or objects on the ground, it's very easy to become disoriented. And once again, this is a physiological process. This is a process that's happening inside your brain. Your sensation of knowing where your body is positioned with respect to the ground and other objects. So spatial disorientation is a leading cause of both CFIT and lock-eye. The conclusion we can make from this is that pilots that are not instrument rated should not fly when visual references are not available due to the increased likelihood of spatial disorientation occurring. So, the use of these visual landmarks during VMC to help maneuver the airplane is going to involve very fast communication using the nervous system. So, this is a physiology topic. So, with that being a physiology topic, but at the same time, with this not being a biology class, I'm not going to teach you the nitty gritty details of how communication in the nervous system works or any other physiological process, but I am going to teach you the surface level details that you need in order to understand what your body does, what it's capable, and what it's not capable of. Okay, so let's say that you're flying by VMC and you're flying through VFR. So you're using visual references like the horizon in order to keep level flight and to keep your correct heading. So when light hits your eyeball, so this is your eyeball right here, that light is going to stimulate cells in the very back of your eye. The very back of your eye is called the retina. The retina contains a type of cell called photoreceptor cells, which absorb light that is entering your eye, such as during the daytime. And the retina cells get excited and send a message through your optic nerve to the occipital lobe of your brain. So your brain receives this electrical message that is conveyed through your optic nerve. The brain receives that message, processes the information, forms a picture that we see, and then the image that we see after this information is processed in our brain, this allows us to send a message through another nerve to the muscles that are in our arms and in our hands. And this is going to allow us to contract those muscles so that we can use our hands and use our arms to adjust our altitude, our attitude, and our bank angle so that we can get the right heading and the right direction that we want the plane to go. So when you're flying VFR, you are maneuvering your airplane based on the things that you see. So because you are changing the direction and changing the heading of your airplane based on the things that you see, we need this communication to happen very fast. And this communication, what I'm trying to get across here, this communication is a physiological process, and that's one of the things we will explore a little bit in this class, in a later chapter, of course. Okay, so just real quick, if we talk about fuel occurrences, so fuel-related occurrences, most of these are going to consist of one of two things. Number one, fuel exhaustion, which is the aircraft completely running out of fuel, or number two, fuel starvation, in which the aircraft still technically has fuel, but for whatever reason, that fuel can't be routed to the engines. So either that is a operation issue on the pilot side, or it's a mechanical issue and the fuel's not flowing from the wings to the engine. So about 95% of fuel-related accidents actually entail pilot error. If you end up with fuel exhaustion, that's 100% avoidable, and that's 100% a pilot error. I mean, like, it's the same thing like if you're driving on the road. If your car runs out of gas, that's kind of your fault, isn't it? I mean, it's your fault that you didn't fill up your car before, like, the lack of fuel in your car, the lack of gas in your car became an issue, right? So that's your fault, right, if that happens to you. It's the same thing with an airplane. I mean, you're talking about a pilot getting cocky, thinking, oh, I can fly a little bit further without running out of fuel. So it's an overconfidence issue. And the thought process behind why you might end up with fuel exhaustion, or you might flip a switch incorrectly to transfer fuel from one side of the airplane to another, these are skill issues. These are psychological issues. They involve the function of the human body and the function of the human brain, which I've said a couple of times already. The human brain and the human body are flawed. They are limited. So understanding those limitations and always siding on caution is going to be the thing to do to mitigate risk of things like fuel-related occurrences. So I've said it already, but I'll say it again. Pilot error is overwhelmingly more likely to be a cause of an accident than some kind of mechanical failure. Now, mechanical failures are kind of fun to depict in popular media and things like that, but they're overwhelmingly rare. Okay, So if you look at this graph here, we can see that things like landings are an issue, other pilot-related incidents are an issue, takeoff and climb, fuel management, maneuvering. A lot of these things involve pilot skill, the ability to make correct decisions, responding to things with quick and appropriate reflexes, responding to visual cues. These are all matters of human body function. So again, this implies a great importance on the study of human factors and the study of human physiology in understanding what your human body is capable of, what its limitations are, so that we can avoid these things from happening. So the previous slide showed us that landings are most likely going to be where accidents occur, even if they are not particularly fatal. So if we go back and look at this, we can see that of the different types of accidents that occur, by far the most likely is going to occur is a landing, but the red bars, which signify fatalities, of the 262 landing-related accidents that were captured in the study, only 3 of them involve fatalities. Okay, but one other thing that you might kind of find interesting here that weather, which is not exactly a human decision-making issue unless you're talking about flying VFR into non-VMC conditions, weather is something that's not technically in our control, right? Even though we can control ourselves not intentionally flying into bad weather, right? So weather, even though it's not the most common type of accident, it is proportionately the most fatal type of occurrence that can occur. So of the 38 occurrences, 29 of them involve fatalities. Okay, so back to what we were saying, the previous slide showed us that landings are most likely to be where accidents occur. So most of the landing accidents still relate to pilot skill errors. They still relate to things like decision making and planning. So these are all human brain related cognitive events that once again, necessitate the study of human physiology and the study of human factors. So one thing you're kind of noticing so far in this chapter is we're focusing on aviation safety, but a lot of what we're doing is definitely justifying the existence of this class, justifying the necessity of studying how the human body operates so that we can better understand how our bodies interact with the aircraft that we fly. Okay, so let's talk a little bit about decision-making errors. We saw previously the importance of pilots being instrument rated to be able to fly into adverse weather conditions. So we call those instrument meteorological conditions, whether it's nighttime or it's cloudy. If you don't have your visual references, that is not VMC anymore. That is IMC. And if you're not instrument rated, like we said before, you should not be flying into IMC. So VFR flight into IMC is without question a major decision-making error. It's kind of like letting your airplane run out of fuel. So it entails either a lack of training or experience or the possession of a dangerous amount of overconfidence. So a study from the University of Illinois showed us that it only takes an average of 178 seconds for a non-instrument rated pilot to completely lose control of their aircraft once visual references are lost. So what that's implying is you may think you're maintaining steady flight, but without those visual references and without the ability to rely on your instruments to maintain controlled flight, you're going to lose controlled flight in about 3 minutes. It's crazy, right? So some 95% of VFR into IMC accidents are fatal. So this is a big deal. So decision-making errors are absolutely a big part, a big contributor towards aviation accidents. And again, this just leads you to believe that, again, you need to understand what the human body and what your brain and what your sensory perception is capable of and what its limitations are. Because again, if you lose those visual references, you may feel like you're maintaining steady flight. You may not feel like you're banking or that you're losing altitude or that your nose is pitching down, but those things are very slight. It's very hard to feel those things. And once you get on a certain bank angle or once you reach a certain attitude, your body adjusts to that and will no longer be able to distinguish a pitch down nose from steady horizon level flight. So this is why it takes so little time for you to completely lose control of your aircraft unless you are an instrument rated pilot. Okay, so a lot of what we've just talked about involves GA aircraft, which is statistically most likely where the accidents are going to occur, right? So let's talk just a little bit about air carrier incidents. So similar to GA, CFIT and lock-eye represent the most common kinds of fatality-causing accidents for commercial aviation, but it's kind of a scary thing if you look at this graph because this is just a raw number of fatalities in the amount of time this study was done, and I can't remember like how far out this study goes off the top of my head, but you're seeing for loss of control in flight, almost 1,200 fatalities, CFIT, 500 about 550 or 560. Unknown 329, runway excursions, which we'll talk about a little bit later. So these bars look kind of scary. It looks like these things are very common, but you need to look at the context down here. Even though the number of fatalities is very high, that is a product of commercial airlines carrying a lot of people per flight. So one accident is going to likely kill 300 people, right? So the actual number of individual accidents is actually very low. Across the whole board here, there were only 51 total accidents, spanning across probably a very long, very exhaustive study done over many years. Yeah, now that I'm looking at the textbook, this was between 2009 and 2018. So we're talking about 10 years of data here. So over 10 years, we're only averaging about 5 accidents per year, and you can kind of do the math to figure out the number of fatalities. So again, a big reason why air carrier travel is disproportionately more safe than GA travel, training, education, and onboard technologies help to drastically reduce the likelihood of these accidents occurring. Okay, so one thing we saw before is that by far the most likely and most dangerous kind of phase of flight where an accident is most likely to occur is in the landing phase. So we saw that borne out in the data that came from figure 1.3. So those were GA data. Well, it's very much the same way for commercial jets as well. The landing phase of flight is very, very, very dangerous and requires a prodigious amount of skill. But for commercial aviation, you're dealing with an extra complication. In commercial aviation, you're flying bigger, faster, and heavier aircraft than you would in GA, so the landing phase of flight is going to be especially tricky. So the most common kind of accident that you see in commercial flight is the runway excursion, which involves either running off the end of the runway because you couldn't stop in time, you couldn't get the wheels down in time, or veering off the sides, either because of crosswinds or just not being a very good pilot, which I'll just leave it at that. So runway excursions are distinct from runway incursions, which you can kind of look up on your own. We're mainly talking about excursions here. But if you look at figure 1.5 from your textbook, what you're seeing here is data that shows the likelihood, or statistically the likelihood, of a fatal accident occurring during different stages of flight. So you have taxi, loading and unloading, you have the takeoff phase, you have your initial climb, your climb after you get the flaps up, you have cruising altitude, you have your descent from cruising altitude, your initial approach, your final approach, and then finally the landing. So if you're looking at just the data with fatal accidents, you can see that fatal accidents are most likely to occur in the final approach and landing, which doesn't seem that much more than, say, cruising altitude or your climb to cruising altitude. But you have to consider the exposure. So this would, like, if you wanted to think of it as a fraction, the exposure or the percentage of flight that each phase makes up is kind of like your denominator. So cruising represents 14% of fatal accidents, but that's actually pretty good considering that cruising represents almost 60% of flight time. You are almost twice as likely to have a fatality in the final approach or landing, even considering they only together make up about 4% of flight time. So you can kind of do the math and figure out that it's something like 100 or 200 times more likely for an accident to occur in final approach or landing as compared to something happening while you're at cruising altitude. So the conclusion we can draw here is that landing and approach represent by far the most dangerous phases of flight, considering how little time is actually spent on them compared to something like cruising. So ultimately, it's important for us to recognize that the advancement of aircraft technology over time has been extremely rapid. Back in the very earliest parts of aviation, you lost airplanes and you lost people in airplanes a lot because the technology wasn't really that good. You had mechanical failures all the time. So if you've ever seen the movie Unbroken, came out in 2018. It's about World War II. It's about a guy who ran as an Olympic athlete, and then he got drafted into World War II, and he flew as part of a B-24 bomber crew. The book that movie is based on details just how common it was for airplanes to go down because of mechanical failure, okay? So the point I want to make here is we don't live in the 1940s anymore where airplanes break down all the time. Now, regular maintenance is, of course, important, but airplane technology has gotten so good that over time, the number of accidents that are being caused because of mechanical failure has gotten really, really low and continues to go down all the time. But disproportionately, as those go down, accidents that are being caused because of human pilot error, the actions of the pilot or the inactions of the pilot, are going up. So aircraft technology gets better and better and better over time, but the human body is as limited and as flawed as it ever was. Humans are not getting better. Airplanes are getting better, but because it still takes a pilot to fly an airplane, the risk of an airplane accident is never going to be zero because of the nature of the person flying the plane. So why is the study of human factors so important? Well, it's important because the data say that the most likely cause of an airplane accident is because of the actions or inactions of the pilot involved, not because of mechanical failure. That's not to say that the engine can't flame out or something might break off of an airplane. Those things can and sometimes do happen, but it is much more likely that an airplane incident is going to occur because of a poor decision-making issue or because of something going on in the human body of the pilot or in their brain, something affecting their cognition. This is why we study this discipline. This is why we study human physiology, so that you can understand the nature and the dynamic of how your body interacts with the different components of the airplane, so that we can get them to work together in harmony to make sure that we fly safely. All right, that is going to do it for Chapter 1. Thank you so much for your attention, and I will see you next time for Chapter 2. So long.